I want to welcome you all to lecture 13 of our Design of Seismic Resistant RCC Building video lecture series based on IS code. In this lecture, that is our lecture number 13, we will be looking at the design and detailing of staircases. The detailing portion for the staircase is a small part, and we will cover that at the end of this video lecture. So you can say this is our 13th lecture on this design course, or this is our third lecture on the detailing course. You can go to our YouTube channel Inquisitive Engineer, and we have 3 playlists there at the moment. First, we started the design of seismic resistant RCC building. Second, we have made 2 videos and we have posted it on YouTube regarding detailing of RCC structures. And the third, we also started with the dynamic analysis, that is response spectrum analysis. And in today's lecture, we will look at some codal provisions regarding staircases, some very basic definitions, some types of staircases, and at the end, we will look at the detailing of these staircases. So let's begin our lecture 13. Before beginning our lecture 13, I want to request you all, if you are finding our videos useful, then to like and subscribe our channel on YouTube, and also share our channel with your friends. We also have a Facebook page, Inquisitive Engineer. I will post the link of our Facebook page under this video, and you can also get information when our new videos are posted through our Facebook page also. So before beginning with the introduction, I want to tell about the reference book that I'm following to make this video lecture, and that is Design of Reinforced Concrete Structures by Ian Subramaniam. Most of the diagrams that I have taken for this video lecture are derived from this book itself, this Design of Reinforced Concrete Structures by Ian Subramaniam, and I want to acknowledge this fact at the very beginning of our lecture. So what are stairs, or what are staircases? Stairs are the means for providing access between the various floors of a building. Stairs are a very important component of a building, and these are the means of providing access between the adjacent floors of a building. The staircase essentially consists of landings and flights. If you look at this diagram here, we have landings and then we have flight for the stair. Our landings, these landings are the horizontal slab platforms, and our staircase may have one or more intermediate landings. So flight and landings are the 2 important parts of our staircase. So this flight consists of an inclined reinforced concrete slab. Since we are talking about RCC structures here, let us say that our flight consists of an inclined slab. And these inclined slabs, are our riser and treads. That is our steps. This vertical portion is known as riser, and this horizontal portion on which we rest our foot is known as the tread. So collectively, this riser and tread are known as the going of staircase. If you project these treads and riser in a horizontal plane, then what you get is the going of the staircase. So our staircase is basically made of slabs and beams. Individually, we have seen the design of slabs and we have seen the design of beams also. So a staircase is nothing but a mixture of these 2 components, slab and beam elements. And the major parts we already talked, landing and flight. You can see more parts of a staircase here. For example, there may be nosing. Nosing is this projected part of our tread. And you have this waist slab thickness. This slab system, or this staircase system, in which you have the steps also made of reinforced concrete. You have a minimum thickness of slab provided at the bottom of these steps This slab is known as the waste slab. And if you look at more detail here, you can see some finishing on the staircase steps. We have 20 mm thickness tiles on our steps, and you can see the section of our staircase also. So before moving to another slide, I want to talk about some parts of our staircase. I want to talk about the definitions on some parts. We have already seen the tread or going of a step. Tread is the horizontal upper portion of a step where our foot rests. And if there is nosing in our tread, then the going of each step is the distance of the tread minus the nosing. For example, if this is our steps here, suppose this is our step, then this whole horizontal distance, we call it the tread, and if you subtract this distance of the nosing from the tread, then you get the going, you get this going of a step. So that is about tread and going. Nosing is the projected outwards or the outward projected portion, and it is mostly concerned with the aesthetics and beauty of our staircase. Riser is this vertical part of our staircase or the distance between two consecutive treads. Flight is a series of steps provided between two landings. For example, we start from here and you go up and then we reach to an intermediate landing. This flight is the steps between these two landings. We call that flight. And waste means the thickness of our slab or the thickness of our staircase slab. So this is generally about or the general definitions of parts of a staircase. So stairs can be classified on two basic types. One is the geometrical configurations and another is structural classification. And in geometrical configuration, you can see different types of staircase here. And geometrical configuration means our staircase can be divided into different types based on architectural considerations. And those architectural considerations may be the accessibility, function, comfort, ventilation, lighting, and other economic considerations. So different types of staircases on the basis of the geometry are here. You can see here. First, in number A and B, we have straight flight stairs. Straight flight, that means you do not have to turn in the middle of these staircases. So our straight flight stairs may have or may not have any intermediate landing. For example, in figure number B, we have an intermediate landing here, but we do not have any intermediate landing in our first step. And another step or another staircase in example or in this figure number C is the quarter turn stairs. Example D is the half turn stairs. Example E is the branching stairs. That means you travel upwards from this flight and you reach a landing, and from that landing you can either turn to the left or turn to the right. So this flight branches into two flights. So this is the branching stairs. In F you see open wheel stairs. G you have open wheel stairs with quarter turn landing, and other you have different types of stairs. For example, circular stairs or these part circular stairs and helicoidal stairs. So among these stairs, these open flight stairs in number D, or you also call this dog-legged stair. This is the most common stair in our residential buildings and also in our other types of buildings. So this is the most common example of staircase in our residential building. We find this quarter turn stair here. At number G, open wheel stairs with quarter turn landing. You can see these type of stairs mostly in our public buildings, in which the width of the staircase is large compared to the residential building. So this is about the geometrical configuration of staircase. And structural configuration, we can divide our staircases into two types. One is the transversely supported staircase and another is the longitudinally supported staircase. And what is the basis for this classification? The basis for this structural classification is based on the predominant direction in which the slab of the stair deflects. So if the slab deflects transverse, that is perpendicular to the direction of movement, then it is transversely supported staircase. And if our slab deflects in the direction of movement, then it is the longitudinally supported staircase. So structurally, staircases are classified into two types: transversely supported and longitudinally supported. First, let's look at some transversely supported stairs. On this left hand side, you can see different diagrams of transversely supported stairs. For example, in number A, if you see, our stair step or our flight is supported between beam on one side and wall on the other side. In example number B, you see that this central beam, which is also known as spine beam, the steps are originating from this spine beam and reaching to both sides, left and right. So our spine beam is at the center and we have steps on both sides of this beam. And in number C, you see that we have cantilever steps here, and these cantilever steps are originating from this spandrel beam. This beam, which is going into the direction of this paper, or going into the direction, perpendicular direction. This is known as spandrel beam, and our steps are originating from these spandrel beams, you can see here, and are cantilevered in nature. So if you think about the deflection of these stairs when certain load acts upon them, you see that, for example, let's see here, this is our first type of transverse stairs. Sorry. The steps are in this direction, that is perpendicular into the plane of this paper, if you think about this, and then our steps are here, supported on beam on one side and walls on the other side. So when certain load acts on this stair, then our staircase deflects in this pattern. Similar is the case here for this number B of this staircase resting on a spine beam. When load acts on our staircase, then it deflects somewhat like this. So we see that while the direction of movement in the stair is in this direction, our staircases are deflecting in this pattern. That means the width of our staircase is acting as the span of our staircase. Remember this, the width of our staircase is acting as the span of the staircase, and then they are deflecting transverse to the direction of movement. So let's see here, in these type of stairs, the slab supports gravity loads by bending in the transverse vertical plane. This bending here, cantilever bending, this is also bending in the transverse vertical plane with a span along the width of the stair. I talked about it before. The width of our staircase acts as the span of our staircase. So when the slab is supported at the two sides by stringer beams or walls, as in figure number A, it should be designed as simply supported. However, its supports reinforcement are to be provided at the top to resist the negative bending moments that may arise due to partial fixity. So although we are designing this transverse staircase as a simply supported slab, we should also consider the negative moments that may come at the edges or at the supports here and here due to the partial fixity of these steps on these supports. So we also have to design for negative bending moments here. Similarly, if we see another figure, the spandrel beam in a cantilevered stair is subjected to equilibrium torsion in addition to bending moment and shear. You can see here, since our staircase is fixed with this spandrel beam, there will be the presence of equilibrium torsion in this beam in addition to bending moment and shear. Similarly, the nature or the behavior of this another type of transversely supported stairs, what it says, although the slab may be spanning transversely, The spandrel and spine beams span longitudinally between the supporting columns and hence have to be designed and detailed accordingly. So you see that our staircase or our steps of this staircase are spanning transversely, but still this spandrel beam in this diagram or our spine beam in this diagram, they are spanning longitudinally because these beams are constructed along the direction of the movement in our stair. Our stair may be transversely spanning, but these beams are spanning in the longitudinal direction. So the design of these beams should be taken into consideration and detailed properly while designing for these types of staircase. So this is about the transversely supported stairs. If you look here, there are more diagrams. We have a diagram of one staircase type in which, in addition to the slab, our steps are also reinforced concrete steps. And in that case, we have two different bars used here. These bars are the nosing bars. These bars are in this direction along the width of the staircase. And then we have this distribution steel here. And these are our reinforcement constituting the steps of our staircase. So this is the case in which our steps are also reinforced concrete. But if we have masonry steps here, then these are simply brick steps. In this case, our reinforcement is, or our main steel is in this longitudinal direction, and then it is detailed accordingly. So remember that in every type of staircase, either it may be transversely supported or longitudinally supported. Our staircase system may be of different types. For example, we may have the staircase with concrete steps, or we may have the staircase with masonry steps. So in this slide we talked about transversely supported stairs. And the second type based on structural classification is the longitudinally supported stairs. Longitudinally supported stair means that the deflection of our staircase slab is in the direction of the movement along the slab. So these stairs span between the supports at the top and bottom of a flight. For example, you see that our staircase may be supported either at the end of the going itself. I talked about going. Going means this horizontal projection of these treads. So this is the going of our staircase. So our longitudinally supported stairs may be supported either end of the going itself, or these may be supported at the end of our this slab, this landing slab, or this may be supported differently. For example, on the edge of landing slab. So we see here different types of longitudinally supported stairs. Let's see. These stairs span between the supports at the top and bottom of a flight and are unsupported at the sides. So we saw here where the supports for these staircases may be. So what happens is that when there is a movement along this slab, then along this movement or along the direction of this movement, our staircase deflects in this way. Our staircase deflects in this way. So the direction of movement is also longitudinal, and the direction of deflection of this slab is also longitudinal. Hence, they are known as longitudinally supported stairs. So in most cases, the west slab may be between 110 mm and 250 mm thick. The thickness of our west slab is more related to the aesthetics and architectural requirements. We do not want the thickness of our west slab to be so greater that it is not aesthetically beautiful. So if the thickness works out to 300 mm, which may not be elegant, a small amount of compression reinforcement may be used in the mid-span to reduce the west slab thickness to about 200 mm. That means we want to use as much as possible a smaller thickness of our west slab. So when additional immediate supports are provided, as in figure number A here, negative bending moments develop at the junction of the landing slab and west slab. That means if our support is provided in this manner, at the junction of this landing slab and this waste slab, negative bending moments arise. Hence, reinforcement has to be provided to resist negative moments developed here. And we will see the detailing later in this lecture itself about the reinforcement required in these areas to resist negative bending moment. So in figure D here, we talk about the effective span of these staircases. I would like to mention here that we will only be designing one type of staircase in the present or for this video lecture series. And we saw at the beginning of this video lecture series, we had architectural plans of the building which we were going to analyze and design. We will look at the staircase present in that building and we will design for that staircase only in this lecture or in the upcoming lecture, I mean in this lecture series. So what is the effective span? Now let's come to some codal provisions regarding the staircases. And the first codal provision is regarding effective span, which is illustrated in clause 33 of IS 456 2004. So there are three basic clauses regarding effective span of stairs in 33.1. The effective span of stairs without stringer beams shall be taken as the following horizontal distance. First, let's see here. Where supported at top and bottom risers by beams spanning parallel with the risers, the distance center to center of beams. That means, if you look at this diagram here, this staircase is supported at the top and bottom riser. Here we have the bottom riser and here we have the top riser. So in these cases, where our staircase is being supported by beams at the top and bottom riser, and remember that these beams are spanning parallel to the riser because the width of our staircase will be in this direction and these supporting beams will also be in the same direction. You may visualize this, think properly and you can visualize this, of course. So in this case, the effective span is taken as the distance or center to center distance between these two supports. So when the stairs span longitudinally and are supported at the top and bottom by beams, as shown in this figure, the effective span is the distance between respective centers of beams. This is clause number A. If you see clause number B, what it says is that where spanning onto the edge of a landing slab, which spans parallel with the risers, a distance equal to the going of the stairs plus at each end either half the width of the landing or 1 meter, whichever is smaller. That means, see this diagram here. When the stairs span longitudinally and are supported by landings on top and bottom, we have landings at the top and we have landing at the bottom, which span in the transverse direction, that is perpendicular to the stairs. Then in that case, the effective span is taken as total going. That means the horizontal projection of these treads, total going G, plus either the half of the width of landing on each floor or each end or 1 meter, whichever is smaller. For example, let's see here, the width of the landing here is twice x is given in this diagram. That means half the width is x. Similarly, the width of this bottom landing is 2 times y. So half the width is y. So if the value of these x and y are smaller than 1, then we take 1 meter. But if these are greater than 1, then we take that value x or y. So let's see here. If both x and y are less than 1 meter, then our span will be g plus x plus y. If x is less than 1 meter and y is greater than 1 meter, we take y to be 1, but we take x to be the same, the value that we have here. So from this you can see that the value of x and y is limited to 1 meter maximum. If it is greater than 1 meter, then we take that 1 meter only. So this will be our effective span of these staircases. So remember, I want to repeat this again. When the stairs are spanning longitudinally and are supported by landings at the top and bottom. And remember that these supports or these landing beams or these landing slabs should span in the transverse direction. Why transverse direction? Because our span of the staircase is in this direction, whereas the span of these two landings are in the perpendicular direction. That means the landing slabs are spanning transverse to the span of this staircase. In these cases, this is the Codal provision regarding the effective span of staircase. And finally, in number C, when the landing slab spans in the same direction as the stairs. In number B, we saw landing slab spanning transverse to the direction of the stairs. But if our landing slab is spanning in the same direction as the stairs, then they should be considered as acting together to form a single slab. And the span determined as the distance center to center of the supporting beams or walls, the going being measured horizontally. That means when the landing slab is spanning in the same direction as the stairs, the effective span is the center to center distance between the supporting beams or walls. For example, if you look at this figure here, our landing slab are spanning in the same direction as our staircase. So the effective span of this staircase will be center to center distance between these two supports. And these supports may be either beams or walls. So these three are the Codal provisions regarding the effective span of staircase. And why do we need effective span? To calculate the load acting on our staircase. So clause 33.1 of IS 456 talks about the effective span of staircases. And after talking about effective span, let us just talk in short about the load on stair slabs. Different types of loads will be acting in our stair slabs. One will be the dead load. And dead load means there are three types of dead load. One is the self weight of the stair slab. That means the self weight of the slab. Another is the self weight of the step itself, and another is the self weight of the finish. And our finishing on our staircase may be either only uh, the finishing, you may either use tiles or different types of marbles or granites. So the self weight depends also depends on the type of finishing or type of finish used in our staircase steps. So these three are the predominant dead load acting on our staircase. And we also have live load or imposed load. So one important condition here is that the imposed loads are assumed to act as uniformly distributed loads on the horizontal projection of the flight. Our flight is inclined at some degree to the horizontal. We will suppose that our imposed loads are not acting on this inclined slab but on a horizontal projection of this inclined slab here. And also if there is any landing, then also this landing. For example, if we have landing at the top and bottom, then we consider the whole span from end of bottom landing to end of top landing, and in this whole length we will suppose that our live load is acting. And live load on our staircase is based on, as you already know, IS 875 part 2. In residential buildings, the live load is taken to be 3 kN per meter square on our staircases. And in other important buildings such as educational, institutional, or business offices or office buildings, we take it to be 4 kN per meter square. And in storage buildings, we take our live load on staircase to be 5 kN per meter square. So this is about the load on stair slabs. And another important Codal provision regarding the distribution of load on stairs is given in IS code 456 clause 33.2. So there are two important clauses in IS code for staircases. The previous one was in 33.1, where we talked about the effective span of our stairs, and in this 33.2 we have about the distribution of load on stairs. What it says is that in the case of stairs with open wells, for example, in this figure, we have open well stair with quarter turn and two intermediate landings. So in case of stairs with open wells where spans partly crossing at right angles occur, the load on areas common to any two such spans may be taken as 1/2 in each direction. For example, you see that our one span is in this direction and another span is in this direction. So you see that this slab is common for both spans. This y-axis, if you consider this y-axis, for this y-axis span and for this x-axis span also, this slab is common. So for this portion here, if we suppose that our uniformly distributed load acting on this span is W, then you can consider half of this uniformly distributed load on each span. For example, on this span, on this x direction span for this common slab, we take it to be W by 2 here. The load is acting uniformly W in this part, and for this common part only half of the load is acting W by 2. Similarly, if you consider this span and again this span here, again this portion of this common slab is common to both of these spans. So instead of taking W for this portion, you take W by 2. So the loading pattern will be similar to this diagram here. In the mid portion, the full load W will be acting. However, in the common portion, W by 2 and W by 2 will be acting here. So we see here the deflection pattern of this span. This is the bending moment diagram, and this is the deflection pattern of this longer span, another bending moment diagram. And in addition, where flights or landings are embedded into walls for a length of not less than 110 mm, if you see here, you can see this diagram. Our steps is embedded into our wall, and this length of embedment is less than or equal to 110 mm. Then a 150 mm strip may be deducted from the loaded area. If this is our full loaded area, then this 150 mm strip may be deducted, and you can suppose that no load is acting on this 150 mm strip, and the effective breadth of the section increased by 75 mm for purposes of this design. So this two, or this one clause 33.2 is dealing with the distribution of load on stairs, and if this comes again during our design of staircase itself in our upcoming lectures, we will see about this bending moment diagram and this load distribution in detail also. So this is about another codal provision regarding the distribution of load on stairs. And finally, let's see here, we have come to the detailing portion of our stair slabs, and in this detailing portion we will only look at a slab spanning longitudinally. And in longitudinal spanning also, we will look at a particular type of staircase with west slab and our steps made of reinforced concrete. So these two are the detailings. In the left hand side, you can see the detailing of a dog-legged stair supported at the ends of the landing. That means if this is our staircase, then our support is here at the end of the landing. And on the right hand side, you can see a dog-legged stair supported at the ends of flight. That means in this right hand case, our support is at the end of this flight. For example, at the beginning of this staircase flight and at the end of this staircase flight. So these two supports are for the right hand side diagram, and these two supports are for the left hand side diagram. You see that there is not much a difference in the detailing between these two dog-legged staircase. I am focusing on dog-legged staircase because we will be performing the design of this same staircase in our upcoming lecture. So there is not much difference in detailing here. For example, if you see here, this is our staircase detailing beneath the ground surface. We suppose that this is the plinth level and this is the position where the staircase is starting at the ground level. We have a footing here similar to our RCC concrete footing, and this depth is not much required here. 3 feet or about 1 meter may be sufficient. And from this ground level or plinth level, our staircase starts, and it rises up from this bottom or from this ground level to our mid landing. And in this, you see that in this detailing, this line or this reinforcement is our main reinforcement, and these black dots, which are the reinforcement spanning along the width of our staircase, these are our distribution staircase. So these black dots seen in this cross section is our distribution staircase, or these are our distribution reinforcement, which are acting parallel to the width of our stairs. And along this slab itself, along the inclined length of this slab, the reinforcement that we have is our primary reinforcement or our main bars. And you see here one important aspect of this detailing is that our main bar, which is at the bottom of our staircase, this is taken to the top and then detailed in this way. And alternately, the reinforcement that is at the bottom of this, or the main reinforcement that is at the bottom of this mid landing slab, is not taken to the bottom of this inclined slab itself, but taken just a little bit forward and then made the upper main reinforcement in our reinforced concrete slab. So you see that we have made some sort of scissor type arrangement here. And this scissor type arrangement is because of the fact that at the junction of this mid landing slab and our inclined stair slab, our negative moments may arise, and to resist that negative moments we have to detail in this way. This is one of the most important part of detailing in the case of staircase. Similar is the detailing for our from mid landing slab to our top landing. You see that this is our 1 floor level here, and this is our mid floor height here. The diagram below shows the detailing of reinforcement for the first flight of our stairs from bottom landing to mid landing, and the second diagram above shows the reinforcement detailing from mid landing to our top landing. So similar is the reinforcement here. Our main reinforcement is placed parallel to the inclined slab of our staircase, whereas our distribution reinforcement is along the width of these staircases. We have a reinforcement to resist negative bending moment. There is a scissor type arrangement here, and the length of these reinforcements here or here, this should be at least equal to the development length of the reinforcement. You can get the general detailing of these staircases anywhere, and you can also follow SP 34 section 10, which includes provisions for detailing of staircases, and you can study about this detailing pattern in detail there also, if the diagram is not much clearer to you or much visible to you here. And for the case of a dog-legged stair supported at the end of flight, the detailing is similar to the staircase slab supported at the end of landing. Only the difference is this additional reinforcement here. Only the difference is this additional reinforcement. We only had this scissor type of arrangement for our staircase slab supported at the end of our landing. If it is supported at the end of our flight itself, then there is some additional rebar detailing here. You can also look at this rebar detailing in this same section 10 of our SP 34 1987. So this brings us to the end of our lecture 13 on this design of seismic resistant RCC building video lecture series. We briefly touched upon the different types of stairs in this lecture. We looked at some Codal provisions, and finally we looked at the detailing portion of our staircase. In our upcoming lecture of this series, we will be dealing with, or we will do some manual calculations and design of dog-legged staircase for our residential building. So we'll meet again soon during our next lecture. Thank you so much. See you soon.